So, today we are going to talk about Taylor's expansion. Who was this Taylor? You can see the spelling Taylor. Who was he? There are many these sort of Taylor names in the scientific literature. His name was Brooks Taylor, and he was a student of Isaac Newton, and he was listening to the explanation Newton was giving about the binomial expansion, that is a plus b to the power n, which you have learnt in high school. Now, he thought whether this binomial expansion idea can be used to make computations of functions easier. For example, if I had asked you to find sine 36 degree, you will not find it easy, because you have few angles, sine 0, sine 30, sine 45, sine 60, sine 90, these are the things given in the table. But if I ask you sine 36 or sine 1 degree or 2 degree or whatever, you will find it little problematic. So, given such sort of functions which are not algebraic in nature, right. So, this type of thing, this sine function or sine x is non-algebraic. So, it is because it is now non-algebraic in nature, is it possible to approximate them through an algebraic function or a polynomial function, where everything is written in terms of powers of some unknown quantity. For example, can I write this as some a0 plus a1x plus a2x square plus say anx and something like this. So, can I approximate it? So, what does it mean is that I cannot compute the value of sin x when x is some arbitrary number like sin 36 by you doing algebraic manipulations like, or using the 4 basic arithmetic operations like addition, multiplication, division and squaring and all those things. So, by approximating, I am being able to immediately give you an approximate value of sin 36 or sin 20 or whatever. So, today we are going to talk about how Taylor thought about this idea to approximate functions which are not so easily computable. Look at a function like this, nice differentiable function. So, let me draw it bigger so it magnifies. So, look at a function like this, and let me take a point here x f x, and I am drawing the tangent line. So, this is your x, and this point that you see is x and f of x. So, if I zoom in here, what do I see? If I zoom in here, I will see that the tangent is almost at this point, the tangent is almost touching, almost very near. The distance between the tangent and the curve becomes smaller and smaller as I approach x f x, whether from this side or this side, which means that if I take x another say y very near x, then f of y can be approximated by computing the value of y on the tangent. So, it can be approximated by computing the point on the tangent, the corresponding point on the tangent. If you look at the equation of the tangent, so if there is a tangent and it has a slopes say m, so it does not matter which is f dash x. So, tangent equation for this curve is y is equal to f of x plus f dash x into y minus x. You take any y here, however near, f of y is slightly higher than y, but may not be very high. So, I can approximate f at any other say y hat, y bob hat, say this is y hat, or y bar, sorry, y bar, as I am approximating is not equal to f of x plus f dash x y minus x. So, this is called the linearization of f, this is called the linearization of f or the first order Taylor polynomial of f. Now, when you know about the linearization of f, it is not a you feel that okay, it is not possibly not a great idea. If I move away a little, then I lose this approximation. This approximation would be very bad and crude. So, let me look at the graph more, this graph more magnified at this point. Okay, this is the tangent and I move away a little. Instead of the tangent now, if I had made the tangent little curvaceous, then I could better approximate the function. So, for example, what I want to say is that now if you add to say f of x plus f dash x y minus x or y bar minus x, here it would be y bar, please note that, plus, so what I have now made is a curve instead of a line. So, it is a quadratic curve, it is some sort of a parabola and it is approximating f much better, that you can see from the following diagram here, that it is approximating f much better. So, I get a curve. So, you can think that I can do something with, so this will be square, I can do something more. So, this is a quadratic term y bar minus x square. So, it is a quadratic curve term in y bar. So, this f of y bar now is a better approximation, it gives a better approximation of f of y bar though not equal to it once you take a quadratic term. Now, essential idea is the following, that okay, let me say that what would happen if f x is actually a polynomial. Suppose I write that f x can be made not, I want to approximate f x with a polynomial. You can observe that these are polynomials. I am not defining a polynomial because this is something very well known. It is, you write these are functions of this form where a0 where a n is not equal to 0, then it is nth degree polynomial. So, what I want to say is that suppose f is this and f is differentiable n times, then what is your a0, what is your a1? Now, let me do one thing, you see f of 0 here is a naught, right. Now, what is f dash of x here? F dash of x here is a1 plus 2a2x plus 3a3 x square plus so on and so forth plus an n x n minus 1. Now, f dash of 0 is a1. So, you have been able to compute the constants in terms of these coordinates. So, then I can compute, now I want to compute f double dash x. F double dash x here is 2a2 plus 6a3x plus an n minus 1 x n minus 2. So, f double dash 0 by half or factorial 2 I am just writing, you will soon see why, is a2. Similarly, you try out f triple dash x, which is now 6a3 plus an n minus 1 n minus 2 x n minus 3. So, which means remaining all will have x, so there will be 0. So, f triple dash 0 by say 1 by 6, which is 1 by factorial 3 is a3. So, give me any function f x which may or may not be a polynomial, then the function g x, which I can write as f0 plus f dash 0 into x plus 1 by factorial 2 f dash x square plus 1 by factorial 3 which is 6 f triple dash one by n factorial f nth degree derivative at 0 x n. So, this g x now, this g x is called the Taylor polynomial of f at x equal to 0. Earlier what this was the second order Taylor polynomial of f at x equal to x. Now our job would be, so if you want to talk about a Taylor polynomial at some alpha, so then you have to write gx is equal to f alpha, so at x equal to alpha, the Taylor polynomial at x equal to alpha, so plus f dash at alpha x minus alpha, the same thing 1 by 2 factorial f double dash alpha x minus alpha whole square plus 1 by n factorial f n alpha x minus alpha to the power n. This is called the Taylor's polynomial at x equal to n alpha. So that is just a wonderful stuff. Now we are going to formally state what is the Taylor's theorem, right. Once we state that, it would be easier for you to understand what we are trying to do. Now you observe that if I want to compute the value of a function at a given point by taking base as some other point, then I can approximate it by a Taylor polynomial. So if you look at up to this part of what I have written down here, this part is the Taylor's polynomial, but what Taylor did was to also compute how much error that it would have. So if I have the function value at fb and I take its approximation using the Taylor polynomial, this part, the part which I have actually given a line across, not the part which I have written down, then Taylor is able to calculate the error. So what he says that if you have a derivatives which are up to n plus 1th order in the interval Lm, right, and rather maybe I would just say continuous derivatives, I would like to add continuous derivatives. So if I assume continuous derivatives up to n plus 1th order and let a and b be 2 points in that interval Lm, then what Taylor shows was that there would be a C which is lying strictly between a and b, it depends whether a is bigger than b or b is bigger than a. So then C would be, say C would be greater than or bigger, strictly lesser than b if b is bigger than a, and just the opposite if a is bigger than b. Then f of b is equal to the Taylor's expansion, nth order Taylor's expansion plus an error term. So this term is called the nth level error. Now if I have, because I have assumed that f has continuous derivatives up to n plus 1th order, then I have something interesting, because once I say that I have nth order derivative which is continuous up to the n plus 1th order, which means that this value f n plus 1 x, this is bounded over the closed interval a b, whatever it is, it could be a, it does not matter. So this is say m. So you can say that the error E n, this m, is bounded by n plus 1 factorial into mod b minus a n plus 1. So the error can also be shown to be bounded in this particular case, and that is very important, because suppose b and a the distance between B and A is small, so small that it is less than A, and as n becomes bigger this part will go to 0 and this part will also go to 0. So, as the n is becoming bigger, your approximations can become very better and better and better. So, if B and A are very close to each other, then by increasing the degree of the approximation n, n plus 1, n plus 2, as you make n higher and higher and higher, your functional values become closer and closer and closer, and that is the key idea about the Taylor's theorem. So, but you can, for example, do some little bit of calculations. For example, say I want to calculate A equal to cube root of 28. I want to compute A is equal to cube root of 28. If I want to compute A is equal to cube root of 28, then it is not so apparent to me what should I do, but I know that cube root of 27 is 3. So, now what I want to do, so I know f20, so f of 27 is 3 if I set if f of x is cube root of x. So, if I said f of x is cube root of x, then f of 27 must be 3. Now I would like to take 27 as a base and expand in Taylor's expansion. So, let me look at the Taylor's expansion gx at a x with base 27 for this function f x equal to cube root of x. So, that will become f 27, which is 3, plus f dash 27. I will not compute the values of f dash 27 stating here, I will just, I have already done the calculation. So, you do not, I will not redo them in front of you, which you can calculate. So, f dash 27 is nothing but 1 by 27. So, let me for the time being not go to higher dimensions and higher orders and just consider on the first order expansion. So, first order Taylor polynomial at 27. So, first order okay. Now, once I have done that, I have to look into the following. So, what do I have? So, I have here 3 plus 1 by 27, which is f dash 27, because what is f dash? Okay, if somebody is uncomfortable with that, let us just do it. What is this? Is x to the power 1/3. So, it is nothing but 1 by 3 into x to the power 1 minus 1/3, 2/3, right. So, basically 2/3 means 1 by cube root of x square, right. Once you do this, you will again see that you get, so x to the power minus 2/3. So, if you put x is equal to 27, so 27, what is 27? 27, so you take 1/3 of 27. So, what is 1/3 of 27? 1/3 of 27 is 3, and then you take square of that. So, that will be 9 and you bring it down because you have a minus 2 and hence you multiply with the 3 in the bottom. So, that will give you 1 by 27. Please check it out yourself, it is a very simple calculation. So, now it is 1 by 27. So, if g, so let me just compute the g at 28. So, that is exactly what I want. Here my goal is now, if I have given the function like this, my goal is to compute f of 28, this is the goal. So, f of 1 is now, f of 28 is now this 28 minus 27. So, you see how nice it becomes 3 plus 1 by 27, which is 3. Of course, cube root of 28 would be slightly bigger than 3 because cube root of 27 is 3. So, it means that this and this is approximately 3.03703. So, this example I have picked up from a lovely book called Approximate approximately calculus, which is published by the American Mathematical Society and written by Shariari. It's a lovely book, which really shows you the power of the ideas from calculus to do numerical approximations. And so this is what you have, but what is your error term here? So your error term here at the second level, so E1 is f double dash c by 2 into 28 minus 27 whole square. So it is again nothing but f double dash c by 2, where c is some number between 28 and 27. Now what c I should take, that is the question. So you might say, okay, this c or all this thing is useless because I do not know your c. So what grade did Taylor do? See, you really can try doing some worst case scenarios with it. For example, you can say that, okay, let me take what should be the value of c which would give me the worst value, right. For example, f double dash x in this case is minus 2 by 9 x to the power minus 5 by 3. So for any x which is lying between 28 and 27, this value would become negative. So that is a very important conclusion. So if this value becomes negative, so if I add this term, then that would be exactly equal to f of 28. So whatever you have to subtract some quantity from this thing to get f28. So the immediate conclusion you get is whatever you have calculated 3.037037 is actually strictly bigger than f of 28, because you have to subtract this quantity for some c that you want to put to get to f28. So this information you immediately get. Okay. One can say that, okay, let me see if I take 27, what would happen? What would be the, what I can do is I would leave you to do an experiment at home. Put 28 here instead of c and see what is the value, and put 27 here and see what is the value. So that would give you two extreme ends, right. So as I move from 27 to 28, this quantity will continue to remain negative and it will go down, and so as a result of which you can actually say between which two values f28 lies. So this could be a little homework, find two values, so that will give a better estimate of f28. So where does f28 is exactly lying, you can pinpoint it. So find two values between which f28 lies. So we have some idea of handling the Taylor's theorem, and then we will start integration in the next week. Thank you very much for your attention. Just have a practice with your assignments, so and keep on looking at the lectures. If you forget something, go back to the lecture and look at it. If there are still problems, put your things in the forum. Our TA and myself will take care of them and answer back to you. Thank you very much.